Yeah,
Uh,
yes, please. We went through small.
that's good. That's good. You have to be doing that for me, okay?
Yes, sir.
Yeah, yeah. All right. Um, I think we can start now. Because
Yes, please.
a lot of machines will it will go off after 1 hour, right?
Ah,
If the
sir.
light don't come, if the light don't come, all right.
Sir, yeah.
So
Yes, sir.
let let's do our best to move forward. When our batteries run down, then we know what we can decide on.
Okay, sir.
Yeah. All right. Today our task is to talk about complex numbers. All right. Complex numbers. So this is what we have. We are introducing ourselves. We have a certain quadratic like this. Are you okay? Like this one. S squared plus 2s plus 5 is equal to 0. And when we use the quadratic formula, which people call it almighty formula, to find it, we know that the coefficient, the A is equal to 1. Then B here is equal to 2. Then C will be equal to 5. When we are using the almighty formula, right? This. So we have minus B plus or minus the square root of 2 squared minus 4 into bracket 1 into bracket 5 all over 2 into bracket 1. Now, when we try to simplify it, we are going to get minus 2 plus or minus root of 16 over 2. And in real number terms, you see, we can as well write this one like this. That is minus 2 plus or minus the square root of 16 multiplied the square root of minus 1 all over 2. And this is what we have now. All right. When we point this on our calculator will tell us that it is math error. Are you okay? It is math error. Math error because in real number system, anytime I have this, S square should be greater or equal to what? 0. So if I have S square is equal to minus 1, how do I solve this? It's going to be difficult. Are you okay? So that one going to be x is equal to square root of minus 1. And in real terms, or in real number system, this one is not solvable. But when we come to the, the complex side, we let complex I represent the square root of what? Minus 1. That is in complex number system. So what we have here, minus 2 plus or minus, okay, 4 root minus 1 over 2 will be simplified to this one. That will give us x is equal to minus 1 plus or minus 2i. All right. So that we can solve it as minus 1 plus 2i, then minus 1 minus 2i. And this we are saying that it is called what? Complex, with the introduction of I is equal to root of minus 1. All right. So we can see that sometimes on the real number system, certain quadratic equations have no solution. But when you come to the complex number system, then we can solve them. All right. How do we represent a complex number? Look at that. We have the first one as A plus the second term as something I. All right. That's what we have here. And we are saying that we are calling this part the rare part or the rare number part. And this part here is called the imaginary part. Okay. It is called the imaginary part. And when we have this, we call this one the what? The Cartesian complex numbers. When we write something like this, the complex form, all right, complex number of this form is called the Cartesian complex numbers. We have the Cartesian one, we have the polar one, okay. We also have another one. So anytime we see a plus bi, this is a complex number, but this is the Cartesian form. Okay. Now let's solve this. Let's solve this quadratic equation. We have x squared plus 4 is equal to 0. Now the solution, let's do this. So we have x squared is equal to -4. Then we are writing x squared here. Ax is equal to square root of -4. Then we come to write it as this. Okay, x is equal to the square root of -1 times 4. Then we write it as, which is equal to square root of -1. Then multiply the square root of 4 so that we can write plus or minus 2i. When we look at this quadratic, okay, has only imaginary part. So we can write it as 0 plus or minus 2 what? I. The real part is not there, is 0, and the imaginary part is there. All right? Okay, so that is what we have. Now let's see. We are concentrating on complex numbers, their real part and their imaginary part. Normally, or standard, we use z to represent the complex number. So z is equal to the real part plus the imaginary part, where we said a and b are all real numbers, and I is equal to the square root of what? -1. Now let's look at this. B. We are saying that for any complex number, this, we call the a part the real part of the complex number. So that is what we write it. We write it as this. That is talking about the real part. Okay. Now when you see this, I am into bracket z is equal to b, then that one we are talking about the imaginary part of the complex numbers. All right. Okay. Now a complex number z here is called a real if the imaginary one is what? Is 0. So I can have a complex number like this. Z is equal to a. It was supposed to be bi. Something is supposed to be here. If this part is not there, then this one will be for only, it will be what? The complex number will be only real. That's what we mean. So we say it is called real when the imaginary part is 0. We can also have a pure imaginary complex number where the real part is also what? It's also 0. All right? It's also 0. When do we say that two complex numbers are equal? When do we say that two numbers are equal or complex numbers are equal? Then let's say we have this, a complex number like z is equal to a plus bi. Then we have another complex number. Let me call this one 1. Another complex number 2, which is c plus di. It is only, we can say 1 is equal to 2 if the real part here is equal to the real part, okay, here. All right. And also the complex part here, b, is also equal to the complex part also here, or the imaginary part there. That is what we mean. All right. So they can, two complex numbers can be what? Equal if and only if both their real and their imaginary part are what? Are equal. So that is what we have made. Now when we go to said, if I write this 2 plus root 3, what is this? Is 1. What is this? 2 minus this. What do we call this one? Making reference to this one.
Difference of two squares.
Is what?
Difference of two
Conjugate.
squares.
Very well. All right. Somebody say conjugate. That's what we need. Look at that. We have root 2 plus root what? 3. So when the sign changes here, this same thing, but the sign has changed. So we are going to call this one the conjugate of the first one. Okay. So here too, we are going to also introduce the conjugate. So if I have A plus BI, what will be its conjugate?
A minus B.
A minus BI. Definitely right. So we are talking about conjugates here, complex conjugates, and we have the complex number as this, and its conjugate is also like this. But look at that. If Z is the original complex number, the conjugate is Z bar. We write a bar on it. So you take note here. That is it, a Z bar. All right. So let's see this. We let Z1 be equal to 7 minus 6i. Its real part is 7. Then its imaginary part is minus 6. Its conjugate, because the original is 7 minus 6i, its conjugate is going to be 7 plus 6i. All right. Now let's consider the second one. Another complex number Z2 is equal to 18i. This one is saying that it is a pure imaginary complex because the real part is not there, it's 0. So we can write it as this, and we say that the real part is 0. Are you okay? Its complex part is what? Is 18, and its conjugate is negative 18i. Are we clear here?
Yes, please.
Again.
I am saying that we have this. We have a complex number of this nature. Then we say that we can write it fully as 0 plus 18i. So what is the real part? What is the real part? The real part is this 0. Okay. Then the imaginary part
It's
will
18.
be 18.
Yes,
Then what will be the conjugate here? The conjugate. What will be the conjugate?
0 minus 18.
0 minus 18, which is negative.
0 minus 18i, which is the same as negative 18 what? I. That's what I said. Are we clear? My
Yes,
sister, are you
please.
clear now?
Please.
Yes,
All
sir.
right.
Yes.
Okay. So when we look at the third one, we realize that the complex number Z3 is equal to 2. And this 2 is just saying that it is what? It is purely real. All right? It is purely real. So if I have Z3 is equal to 2, I can rewrite this one to be 2 plus 0 what? I. 2 plus 0 I. Now, what is the real part? The real part here of this is 2. What is the imaginary part?
0 I.
0 I.
When we are writing the
0.
imaginary and we don't add the I, okay? So the imaginary will be 0. Good. So what will be the conjugate?
2 minus 2 minus
It is
0
2.
I.
2 minus 0 I, which we can write as what? Also 2. Are you okay? Because the negative is at the back of the 2. So that is what we are trying to do. That is it. Simple and short. All right? Simple and short. All right. Now let's consider some properties of complex conjugates. Complex conjugate. Now we are saying that when we add two complex numbers together and we find the combined conjugate, it's equal to finding the conjugate of what? The first one and also the second one, and now sum them up. Is the same. All right, so that one will give me the same answer. If I have Z1 A plus BI, then Z2 is equal to C plus DI. They say when I add these two together and I find their conjugate, that is this one plus Z2, I find their conjugate, it should be the same as finding the conjugate of Z1 plus the conjugate of Z2. This one should be equal to this. All right. If it is product, you are multiplying. It should also be the same. All right. And if we are dividing them, it should also be what? The same. Provided the denominator there is not equal to 0. So this is the theory. For any two complex numbers, Z1 and Z2, we have these three as being true. All right. Remember, one day we'll ask you to just show. So we are going to try one. Now let's see. We have Z1 and we have Z2, where A, B, C, and D are all what? Real numbers. Good. Now let's add them first. All right. We are adding them. Now when we add, that is, we are adding this one to this one, finding their conjugate. Okay. So we write the conjugate of it. That is A plus BI plus C plus DI. Now when we are adding, we add the real part to the real part and the imaginary to the imaginary. So the real part here is C, the other real part here is C. So that one will be the real part A plus C plus B plus DI. That's the imaginary part. Remember, there is a bar on their top. We say we need their conjugate. Okay. Now, if we want to remove the conjugate, look at that. If I have the conjugate of something, conjugate of this is equal to A minus BI. When I remove the conjugate, it will give me this as A plus B what? I. All right? Okay. So we have here, because there was a bar here, we put the bar there. They say we should add them and put the bar on them. We are finding the conjugate of the sum. So this is, the sum is what we have here at the third line. This is the sum. And we need the conjugate of that sum. So if the sum is A plus B, A plus C into bracket, plus into bracket B plus D, and now we need the conjugate of that one, definitely it's going to be this. That's going to be A plus C minus B plus D. Are you okay? Or I. Now we want to do rearrangement. Let's do it here so that we will see. I have Z plus 2. And we are having A plus BI plus also C plus DI. What should I write as an addition? A plus C, okay, plus B plus D. Then I put I here. This is what I have. But look at that. They brought this one here. So they needed the, the conjugate of the sum. So let's put it here. This is the addition. Then they need the conjugate of this one. So what do you think the conjugate will be? The conjugate is going to be A plus C, then minus B plus D. This is the conjugate of this. Now let's rearrange. All right. Now we are taking the first to the first here. So at the end, it's going to be A minus BI as 1. Then plus, now it's going to be what? C also minus B what? I. What do you see? When we compare this one to this one, you see that if Z1 is equal to A plus BI, its conjugate is A minus BI. That is this one. Look at that. this one becomes the conjugate of this. All right. So we can say that this one here is Z1 conjugate. Then plus, when we look at this one is also the conjugate of Z2. So that one also becomes the conjugate of this. So in short, if I add something like this and I find their conjugate, it should be equal to finding the conjugate of this, finding the conjugate of this, and add them together. That is what we have done. Are we clear? Are we clear?
So the latter part again.
All right. Okay. Let's see. So we are saying that first, what we want to do is that we are adding two things together and find their conjugate. All right. So what did you do? We needed a sum first. So the sum was to add them. All right. That is A plus B, I plus also A plus C, I. So we added them and get A plus C into bracket, A plus D, I. Remember, they say we should find the conjugate of the sum. So the down one here is the sum. So what is its conjugate? And we say that for the conjugate, the sign in the middle there changes. So the conjugate of this one now produces this. That will give me A plus C minus B plus D, I. Now here, we have to rearrange them. We are separating them into individual, complex numbers. So when we do that, we take the first real here and go and take it imaginary here. But the sign between them is minus. So here is going to have, A minus BI plus C minus DI. We have it here. Now we are comparing this one to the original. The original one is A plus BI. And what we've gotten here is A minus B what? Minus BI. Meaning that, this one is the conjugate of this. So this one, its conjugate is this one. Are you okay? This one. The conjugate of this is what we have gotten now here. So we are just saying that when I get this one, it is the conjugate of this. That's what we wrote down here. Now, when we look at C minus DI here, that one is also the conjugate of C plus DI. So we are saying that the conjugate of this is equal to C minus DI. That is what we wrote also at the down here. So we are telling ourselves that this one, what we got up here, is the conjugate of Z1, and what we had up here is the conjugate of what? C2. So in short, we want to say that when I take the sum of two complex numbers and I take their conjugate, is the same as taking the conjugate of the individual and sum them. Is it clear now?
Yes, please.
Yes, please.
The last two terms over there, is it Z conjugate of Z1 plus?
Yeah, conjugate of Z1 and conjugate of Z2.
Okay.
All right. Okay, so the same thing applies to when they are multiplying. All right. When they are multiplying, this multiplication, you need to take your time and do it. All right. Now we are going to look at something here. Now let's go here. Let me give you this. A plus BI multiplying C plus DI. Now let's do the expansion or distribution. Now this one is going to multiply everybody here by the JHS approach plus also BI multiplying everybody here. Now let's do. This one will give me AC plus AD. Yes.
Is the A multiplying by
Oh,
C
okay.
C
Oh.
plus AI or D?
Pardon.
You wrote something, but it wasn't clear.
Oh,
Uh-huh.
okay.
Please,
Is it AI?
the DI is like AI.
Oh, sure. Okay. This one. Okay. Let me write it well, please. Let me write it well. Good. All right. So we are having this. What we are doing is that we are multiplying the two. Okay. We have here A plus BI multiplying C also plus DI. Do you agree?
Yes, sir.
All
Yes,
right.
please.
Now let's do. I will use this one to multiply this. That one will give me AC. Then this same A will go and multiply this one. So I have plus ADI. Okay. Now I come here. This B is multiplying this one. So I'll come and write maybe CBI. All right. Now plus, look at that. B is multiplying D. That will be BD. But I here is multiplying I here. So that one become I what? I square. All right. Now let's look at something. We have said somewhere that I is equal to the square root of -1. So what will be I square? I square will be
-1.
so it's going to be -1. So if this one here is going to be -1, then the -1 is going to affect this one, right? Hello?
Yes.
Yes.
So it will convert this sign here into what? Negative. Do you agree?
Yes, sir.
Oh,
Yes, sir.
because if I have BD multiplying by -1, won't it be negative BD? Won't it be so?
Yeah.
Yes, sir.
So if that is the case, then look at that. We are going to rearrange them. Those with I attached and those without I attached. So I am bringing this one and that one together. So that one will give me AC minus BD into one bracket. Then I come to write plus, let's see. We can write AD plus CB, or I can write this CB plus A. Okay, let's say AD. AD plus C also B, but there's I attached here. All right. So this is what I'm writing. AC minus BD, then plus AD plus CB, but here there should be I attached. And this is what we have. So that is what we did here. Look at that. All right. This is what we have. And here became negative. The negative is because there was I multiplying I, making it I square, and turn that one into what? Into a negative. Now it is the product of 1 and 2, and we find their conjugate. So if the product now ends as here, what do we need? We need the conjugate of the product. All right. So the conjugate of this product will be the next level. All right. What is inside the bracket is AC minus BD. Then the sign will change to minus. Are you okay? So that we have BC plus ADI. Now we want to rearrange them into single, complex. So what do we write? We are taking A minus BI times C minus DI. That's the rearrangement from here. Okay. And when we get this, what do we see? The original one is the one with A plus BI. But what we have gotten here is A minus what? BI. What is this? This one is the conjugate of the first one, is the conjugate of this. So that's why we wrote that. this one is equal to the conjugate of the original. All right. And what is this one? This one is also equal to the conjugate of the original. So we have written that this is equal to the conjugate of the original. All right. So in short, we are saying that when we take the product of two complex numbers and we find their conjugate, it is the same as finding the conjugate of the first one, finding the conjugate of the second one, and now you multiply them. That is all what we are trying to show. Are we clear? Are we clear?
Yes,
Am I
sir.
online? Yeah.
Yes, sir.
Okay. So that is it. Please, you are to try this one. The third one is that when I find the division, Z1 divided by Z2, whatever I get, I take its conjugate. All right? Take its conjugate. What are you going to get? Now, when you are done, find the conjugate of Z1 and also go and find the conjugate of Z2 and divide the conjugate of Z1 by Z2 and see whether what you did here will not be the same as that. Are you okay? It's going to be the same. So you try that one. All right? Okay. Now let's come to operations. Operations, we are talking about arithmetic on numbers. When two or more complex numbers are given to you and you are adding or subtracting or multiplying or dividing them, what are you going to get? Are you okay? So we can what? We can just apply an operation on two complex numbers. We can be asked to add. We can be asked to what? Multiply or subtract or even divide them. Are you okay? That is what we want to do. But remember, we have said this one. I1, I square is equal to this, which is equal to this, and is equal to that. Okay, what is I to the power 3? We are saying that we can write it as I squared times I, and we know that this I square here is minus 1. Then this I is there, so it is minus 1 times I, which is going to give us I what? Negative I. Good. If we are taking I to the power 4, we know that I square is minus 1, another I square is minus 1, so we multiply it and we are getting that. All right, we are getting this one. When we are given negative I and we square it, negative I and we square it, we can just do it like this. We bring the negative 1 outside and square it, then we square this one. When we square negative 1, we get 1. But when we square I, we get negative 1. Therefore, that one is going to give us negative what? 1. All right. Okay. Now let's look at this. We have done this one for us. I3 has already been done. I4 we know. Now I to the power 23. All right. All the time, our concentration is whether the power is even or it is odd. We are taught in real number system that anytime we have a negative number, are you okay, to the power odd number, it gives us the answer is negative. But if we have a negative number to the power an even number, we get what? Positive. Are you okay? So the interest is that we know 23 can be factored as 1 and what? 22 using the indices approach. All right, using the indices approach. So we write it like that. So we also write it as this. All right, we write it as I times I squared times 11 because indices, we know that 2 times 11 will give us what? 22. All right. Now, when we square the I, we know we are getting negative 1. So we have it. And negative 1 to the power odd number. 11 is an odd number. So that one will give us -1. All right, it's going to give us -1. And we multiply -1 by I, we are also going to get this one. All right, we are going to get this one. All right, so that is what we are trying to do. Now, when I is given to us, 9, look at 9. What do? We are doing this one as 1 times I 8. Then we have I times the 8 will be I to the power 2 multiplied by 4. Okay, so I square is -1. Then the 4 here is all an even number, so it will convert that one into positive. All right, and when we multiply, okay, I times the 1, we are going to get this. We are going to get that. Now, this is also what is given to us. -4 over I to the power 9. We have already done I to the power 9 here. I to the power 9. And we had I. Okay, we had I. So what are we trying to do? So look at this. What are we trying to do here? We write this one as this is equal to 4 to the power I. Is this one correct? Let's check. This one. There's a problem somewhere. Where is it?
You should have -4 over I.
-4 over I. All right. That's what my brother is saying. -4 over I. So it's supposed to be this over -4 over what? I. Why are you saying so?
So I think because we are saying that the I9 is we got I.
Yeah.
So the -4 on I9. So we replace the I9 with the I.
That is it.
9.
That is it. Thank you. All right. So that is it.
Sir, please, I have a question.
Uh-huh.
Can you go back? Sir, so please, can we conclude that when the power is even, it means that we are going to get positive.
Uh-huh.
And when the power is odd.
When the power is odd,
then
you have to be very careful. That one works.
No.
That one works when we are in the real number system, right?
Okay.
Look at this. 23. Is it odd or even?
23 is odd.
Odd. We had what?
Negative
9.
I.
So
9
it's odd.
Odd. 23 is odd.
Yes.
And we had this. And what of 9?
Now positive.
Are you okay? So
Yes, sir.
so in complex, we have to be very careful. All right. For the real numbers, some things are just straightforward like that. Okay.
Sir.
All right.
Okay, sir.
Okay, sir.
Sir,
Yes, my friend.
please, the -4 over I, do we have to rationalize it by multiplying it through by the conjugate negative I?
I like that, my sister. I like that. You have rationalized it, right?
Yeah.
So when you rationalize it, what happened?
It becomes negative I squared, because negative I will multiply the negative I, and then -4 will multiply negative I, where they are getting 4I over negative I squared.
So that one will give me, you see, like a rationalization. So that one will give me, then this your answer is correct, isn't it?
Yeah.
Yeah. So look at this. I don't want to talk about it. Look at this. The question given us was a negative there, a negative is there, right? Okay. Now 9. Where are they picking this one from? The 9, they wrote I straight. Look at that. I here straight. This is what they did. So now it gave us negative 4 over I. This is where they are rationalizing it. They use the conjugate of the I. That is negative I to rationalize it. Okay. So now the top now becomes 4 times negative 4 times negative I. Definitely, we are going to get what? 4I. Now, when I multiply this, 1I multiplied by negative I will give me negative I squared. All right. Meanwhile, I know this I squared also to be a negative 1. So that one becomes negative 1. And that one will definitely give me what? 1. So this is supposed to be over 1. And this is correct. It was just there, live for you to see. Are you okay? It was just there, live for you to see. So if you don't rationalize it, hello, when you write it like this, well, it becomes an answer, but we don't need this one. Listen, when we are writing the what do you call the complex numbers, we need the real part and the imaginary part, and all the time the imaginary part is with I. It is not with over I. Are you okay? So you may write this one negative 4 over I. This one cannot be termed as the imaginary one. We are writing A plus BI. So we want the B to come up. So for you to be able to do that, rationalize it. Are you okay? Rationalize it. And that one will send this one to this. That's what, so that we get the imaginary part like that. Are we clear?
Yes, sir.
Yes, sir.
Thank you very much. All right. Now, we have 2, and we are adding them. We have said that when we are adding, I will add the real part to the real part and the imaginary part to the imaginary part. Okay, so to be able to add Z to W, we are going to add the real part, which is A plus C, then the imaginary part B plus D with an I. When we are subtracting, it's the same. Are you okay? We subtract the real part, and we also subtract the imaginary part. Okay? Well, we are multiplying. This is what we did. When we are multiplying this is what we are going to get. This one here, this square is going to be negative 1. That forces what this one to be negative. And that is it. So now this one become a real part without I, and this one will also be a real part because the I would diminish. So that one comes here. Then the one with the I, the imaginary one, will be grouped like this. Are we there? So that is it. Okay, that is it. Now let me take this one. I want you to add this Z to W. What will I get? Straightforward. We are adding
1 negative 2I.
1
Negative
negative 2I. Let's see. And that is it. Okay. Then when we are subtracting, we are also going to get 5 negative 6 what? I. All right. 5 negative 6 I. All right. Then when we are multiplying, the 3 will multiply negative 2. That same 3 will multiply 2I. So this one take care of everything here. Then minus 4 will also multiply. Okay. Minus 4I is going to multiply 2, negative 2. And that one is going to give me this. All right. Then minus 4I is multiplying 2I. So that one gives me this. And this I here, that is I times I will give me I squared. This I squared here Now, what is here is going to be negative 8 multiplied by negative 1. So it will turn to positive 8. So that is positive 8. So we have negative 6 plus 8i plus 6i plus 8. And definitely we are going to have 2 plus what? 14i. That is what we have. Is it clear?
Yes, sir.
All right.
Sir, please, I
So
have a question. With the
yes, please.
multiplication,
Uh-huh.
when you expanding,
Yeah.
3 by negative 2, then the 3 will take on the 2i, 3 times 2i. Then
So here
the plus over the before the one that you have underlined. The plus, how did we come about the plus?
okay, now look at this. This one is multiplying this. Are you okay?
Yes, please.
Then this sign, the plus in the second bracket,
Okay.
will come before I deal with this one. Are you okay?
Okay.
All right. Thank you. Now let's talk about, so we know addition, we have talked about subtraction and subtraction. Let's talk about division. And division, we are saying that here it is slightly what? Different. Okay, division is slightly different here. Okay, how do we express this? We are expressing this one like that. Okay, now look at that. It is A plus BI divided by C plus DI, and we are to express this whole thing, this rational function, in the form of this. All right. So, like my sister said, if that is true, then let's use the conjugate approach and rationalize it. Okay. So we are going to use the rationalization method so that we'll bring it like this. So if I have A plus B, I, and C plus DI, instead, we know that we all the time rationalize it using the conjugate of the denominator, right? Conjugate of the denominator. Now let's look at this. If I have Z to be A plus BI, and I have its conjugate to be A minus BI, when I multiply you by your conjugate, the answer that you get becomes the real part square plus the imaginary part square. That is what you get. Anytime you have a complex number, and you take its conjugate, and you multiply, okay, the rational number by its conjugate, the final answer should be the real part square plus the imaginary part what? Square. All right. That's what we want to do. That is something we should know. So we'll come to that. Now, what do we want to do? We want to rationalize it, meaning that we will take the denominator, find its conjugate, multiply both the numerator and the denominator by that conjugate. All right. So what is the conjugate of W? The conjugate of W here, where is W? Yeah, W is C plus DI. So its conjugate will be C minus D what? I. So therefore, we are multiplying the numerator by that. That is what we have here. And also multiply the denominator by the same thing. Now, the down one here, we know that we are multiplying U by your conjugate. So what are we supposed to get? We are going to get C squared plus D squared. Now, our interest is to deal with the numerator. And the numerator will also have what we have. Look at that. When this one multiply this, we are having AC. Are you okay? Now, okay, let's do it. I want us to do this one. It is AB C minus D. Let's do it together. A plus BI multiplied by C minus DI. When we multiply, what are we going to get? AC, this multiply this one, then this sign is minus ADI. Okay, so this one has taken care of the 2. Now we want this one to also take care of this one. But the sign here is plus. Now we are going this one and this. So that one becomes CBI. Then minus BDI square. This I square here will be minus 1. So it's going to convert this sign into positive, right? So we are going to have AC plus BD. Are you okay? So this one and this one has been taken care of. Now let's look at here. Because there is I here and there is I here, we have to put them into a bracket. So 2 things. When I write minus here, then it's going to be ADI minus CB. Okay, the I should come out. This. No I here. No I here. If I factor this negative out, then here should be negative, so that when I multiply, negative multiplied by this will give me negative, and the negative multiplied by negative will give me positive. Or in simple terms, I can do this. I can decide to write the positive one first. So when I have this, all right, when I get here, and I don't want any trouble, anyway, whichever one that you write is correct, I can write plus CB minus AD or what? I. Whichever way you write it is correct. All right? Whichever way you write it is correct. So look at that. So we brought this one first before the one with the minus. So this is what we are going to get. Now, when we get here, are we done? We are asked to write it the real part and the imaginary part. So let's try something here and see. Okay? Because this one will be numbers. This one will give us one thing. This one will also give us one thing. This one will give us one thing. And we divide here by the denominator. Also divide here by also the denominator. And we will be getting our answer. So Z is 3 minus 4i. Then W is minus 2 plus 2i. All right. Now, what do we want to do? The denominator, they say we should find Z divided by W. So then let's find the conjugate of...
Hello, sir. Someone's
Yes,
camera is on and the person is showing. The person is showing. Someone's camera.
All right. Is it okay now?
Yes, please.
All right. Thank you. Okay. So now we have to find the conjugate of the denominator. And look at that. If I have minus 2 plus 2i, its conjugate will be minus 2 minus 2i. So we use that one to rationalize it if we would borrow that idea. So that is it, and also that. We have said that the denominator, we square the real part and also square the imaginary part, or even there, you can expand it. Are you okay? You can expand it as well. So you can expand the top, which is 3 multiplied by negative 2 will give me negative 6. Then minus 3 multiplied by 2 will also give me negative 6i. Then minus 4 multiplied by negative 2 will give me plus 8i. Then minus 4i multiplied by negative 2i will give me, it's supposed to be give me 8i squared. Are you okay? 8i squared. That is what is there. But we know what I square is. When you do the denominator, you will see that you also have the first one square. That will be 4. That is minus 2 will give me 4. Then I use minus 2 to multiply minus what? 2i. All right. Something is there. That will give me minus 4i, plus 4i because minus minus. Then I multiply 2i multiplied by negative 2. That one will give me also negative what? 4i. Then negative plus 2i multiplied by negative 2i will give me negative 4i squared. When we look at this, the middle one takes itself away. Minus 4i plus 4i all the time. That is why we say that in simple short terms, just square this one. Okay, plus you also square the imaginary one. You get the same thing. All right. So the denominator there will give us 4 plus 4, which will give us 8. Now let's look at the numerator. The numerator here, this one is going to give us negative 8. So I have negative 6 and negative 8, giving me negative 14. Then I have negative 6i plus 8i. That one will give me 2i. So in short, now I want to write it as a complex number. That's the real part and the imaginary part. So I'll have negative 14 over 8, which will reduce to negative 7 over 4, plus 2i over 8, which will also give me I over what? 4. And I have done justice to what I've been asked to do. All right? You have done justice to what you have been asked to do. Are we clear? Is it clear?
Yes, sir, I have a question.
Yeah.
Sir, I have a question.
Yes, let it come.
Yeah, sir, the conjugation form. The conjugation.
Yeah.
The formula is a squared plus let's say b squared. But that's
Hello, sir.
the plus is
Yeah,
not minus.
Is it minus?
The plus is not supposed to be minus.
The conjugate form?
Yes, please.
Yeah, when you go to the real system, you are going to make it minus, right? But we are into the complex system. Let's open it up and see. All right. Okay, so that is why we said, now let's see something. Okay, let's try here and see. When we square this, plus we square this, what are we going to get? That will be it, right?
Yes, sir.
If we have made it negative, what are we supposed to get?
0.
0. Are you okay?
Yes, sir.
Okay.
Yeah. So that is it. If it will confuse you, you just expand. Do the expansion by yourself, and you'll get your answer.
Sir.
Are you okay? Yes.
Sir.
Yes.
When you have 2i squared, the 2 squared and the I squared. So the I squared is negative 1. Therefore, where the negative is, the negative 1, which is the I squared, will make the center here positive.
Okay. Let's see. Okay, let's see. So I've seen it. So let's move. Let's clarify that. Okay, it's good you have seen it. So okay, let's see. So then it should be. Now we are talking about this. So it's where we square this. All right. And we also square this. Yeah, that's what I'm saying. You see, this one, if you are picking it not using the eyes, if you are not using the eye, look, when you are dealing with what do you call said, that one, the negative works. But when we are dealing with this one, look at that. Because there is I attached to it. If I take this one straight, like I'm not attaching, if I want to use that idea and I take this one straight and I square it and I do minus, also this one straight, it's going to give me what? 0. Are you okay? It's going to give me 0. So if I want to use the shortcut way, it is the real part square plus the imaginary part square. That should give me the denominator. But if you want to expand it, look at the expansion. And what is making that? It is taking care of, look, when I square this one, so here we are saying that we don't want to add any I to it. That's what this is a shortcut way. But if you are expanding it, then you can go your true way. This one will multiply this to give me 4. This multiply this to give me also, you get this one. It should give me 4i. All right. Then this multiply this will give me minus 4i. And when this multiply this one, I'll get minus 4i squared. But because this here, I square is minus. Are you okay? And I said that this one will go off. So now what is going to be left is 4. Are you okay? Minus 4 multiplied by negative 1. Are you okay? And by that, what are we getting? This negative will affect this one to be 4 plus 4, which is equal to what? 8. All right? That is what we need. So we are saying that anytime we want to follow this shortcut, look at that. Multiply something by its conjugate. When you go through, it will be this. This is b squared. But this I square will let this one be positive. And this one will cancel everything. So in short, you can just take the real part and square it. Then you add it to the square of the imaginary part. It shortens everything for us. Are you okay? Are you okay? But in real terms, like when you are dealing with said, like 2, let me see. Like in said, I have 2 over 1 plus root 2 multiplying by the conjugate 1 plus root 2 a minus root 2 over 1 minus root 2. Here, when you are using it, then it is this a minus here 2 multiplied by this. But here we take this one. This is real number. We take this one square minus whatever is here what square. There is no I there. So in real number system, we use the minus here. But in complex system, we are not using the minus. Are you okay? Are you okay?
Okay.
Are you okay?
Yes, sir.
Yes, sir.
That's the difference. That's the difference, okay? Then let's concentrate here. We are talking about complex. So the complex, we say take the real part and square it, add it to the square of the imaginary part, and you are going to get what you want to get. All right, good. Now we are also saying here that the associativity property also works here. All right, so this one works. A z 1 plus 2 plus 3 is the same as 1 plus into bracket 2 plus 3. And when they are multiplying, we fix first and second and multiply it by the third. We can as well also fix second and third, and we multiply first by the fixed second and third. All right. Then commutativity is also true. The first plus the second should be equal to the second plus the first. And the product of the first and second should be equal to the product of the second and the first. All right. Now the distributive property also is conserved here. All right. When this one is out, it is Z1 multiplied by Z2 plus Z1 multiplied by Z3. So for complex numbers, we are saying that all the arithmetic rules are applied. Now, an exercise here. Show that the complex numbers are commutative. All right. So you are going to show that they are commutative. All right. So for a complex number z, which is a plus bi, then we take its conjugate. We have said this one already. Look at that. Let's compare the original with its conjugate. Now, what is the rare part of the conjugate? This is the rare part of the conjugate. What is it?
A.
Okay, so and what is the rare the imaginary part of the conjugate?
bi
minus b
Minus B.
Minus b I or minus b is minus b. Now let's look at this statement. We are saying here that the rare part of the conjugate is equal to, are you okay? The rare part of the original complex number. Are you okay? And the imaginary part of the conjugate is negative of the imaginary part of the original. That is what we have said here, which is true. All right, which is true. Then we are also saying that then this means that if the complex number is just real means that the imaginary part is not there. If it is just real, then the original is equal to its conjugate. That is true. And also, if it is purely imaginary, meaning that z, its imaginary is b, and its conjugate will be minus what? B. Then we can say then here that the conjugate, are you okay? The imaginary of the conjugate is equal to the negative of what? The imaginary of the original. This thing that we have said here, that is what we have written, is the same thing here. So this one means what we have said here. All right. Now we are also saying something. When I add u to your conjugate, we get 2 multiplied by your real. Is it true? Let's see. Let's use this one to do it. Let's use this one. I have you add the z to its conjugate and tell me what you are going to get.
That will be 2a.
That will be 2a. All right. So we are saying that when we add z to its conjugate, we are going to get 2a. Then the 2a is the rare part of z. So that is it. When we subtract, what do we get? We are subtracting. What are we going to get? Yes. A hand is up.
2bi.
2bi. That is it. And when we multiply u by your conjugate, we know that it will be a squared plus what? B squared. Good. What is the conjugate of a conjugate? A conjugate of a conjugate. What will you get?
The real.
The real. Good. That is it. You have to get the real. All right. You have to get the real. So that is what we are trying to do. Yes.
Please, can we take an example for us to prove the 3 properties that you are talking about so that we get the real understanding?
All right.
On different board.
Like this one's, right? The 3. Okay. Let's take this. Let me take a rare example. Like I have z1, let's say z is equal to a plus bi. Its conjugate is equal to A minus B I. I am adding this. Okay, let's use Z. Z to 8 conjugate. So that one is giving me A plus BI plus A minus BI. All right. We said that when we are adding, we can only add the real part to the real and also add the imaginary part to the imaginary part. Now, when I am adding A to A. That one will give me 2A because A plus A will be equal to 2A. But when I am adding the imaginary part, then I have this. B minus B I. And this one will give me 0. 0I. So it's not there. So when I add something to 8 what? 8 conjugate. It is only the real part that adds because the imaginary part are opposite. One is positive and one is negative. So it carries it away. Are we here?
It's very clear.
Okay. Now let's do the minus. We are subtracting. This time we are subtracting. So if we want to subtract, I'm coming right now. If I want to subtract, yeah. Let's do the subtraction now here. This time it is subtraction. Here. So I am subtracting. So now that one becomes Z minus this. A and A. So that one becomes A minus A. Are you okay? Is this one against this? Then this sign here is plus. Then I come here and write, look at this. I have B here. This minus is here. Are you okay? But the B also there is already a minus. So now I write minus B. And this one will turn it to plus. This one goes away. So I have also 2 what? Also B. That one also works here. Are you okay? That is
So it's not BI. It's not
okay?
2BI.
Yeah, it will be 2BI. Yeah, that is it. So that is it. Are you okay? That is what we are talking about. Is it clear? So that is it.
Yes, sir.
So and this one we know. But we are also saying that the conjugate of a conjugate is equal to, and my brother said is the real. Look at this. The real one, Z, we are saying is A plus BI. Its conjugate is A minus BI. Then the conjugate of the conjugate, this one, the conjugate of this conjugate here will be A plus BI, which is the original complex number. Okay, that's why I said the conjugate of a conjugate now comes to the original. So that is it. All right, that is it. So we have this. All right. Okay, now let's look at this. We are talking about complex plane. We can plot these things. All right, graphically. We can use graph, okay, to represent complex numbers. And that name is what? The complex plane. All right. Somebody call it the geometry of complex numbers. Or we also call it the Argand diagram. Okay, the Argand diagram. So we are going to talk about the vertical one, the horizontal one, and also the origin. That is the 3 main things we are talking about. This horizontal one takes the real part. So it will be minus A here and A here. Then here will be BI here, minus BI. Are you okay? So the horizontal here is talking about the real system, and the imaginary system is taken by the vertical. All right, it's taken by the vertical. So anytime we are plotting A and B, so the A will tell us what steps on the real, and the B is also measuring from the hot, the vertical, which is the imaginary one. Are you okay? That is what we are trying to do. So we said that a complex number this can be translated to the point AB in the standard Cartesian coordinate what system, and vice versa. Every point here represents a complex number Z. This picture of the graph is called the complex plane or the Argand diagram. On the graph, the x-axis is the real axis. Are you okay? Representing the real part. And also the y-axis also represents what? The imaginary axis, which represents the imaginary part. So when I write something like this, look at that. 3 steps on the real line. So it is from origin 1, 2, 3. So that is it. This way 3. Vertically up 2. That is 1, 2. So that is it. So we are representing it like we represent vectors. 3 steps on real, and what do you call 2 steps on the vertical. That is it. Becky, wait to me. Now, when we look at W, here, the imaginary one is -2. So this way, -2. Then the imaginary one is 4 up, 1, 2, 3, 4. So that is how we are plotting it. Like we are plotting our coordinate on the real line or the normal plane. Okay. Now let's look at V. The real one is 5, but the imaginary one is 0. Okay. And that one is this. Okay. Then if this Z is 3 plus 2I, what is its conjugate? What will be the conjugate? Hello?
3 minus 2I.
3 minus 2I. Now, when we are plotting this one, it is 3 positive on the X minus 2. So that is it. 3 and the -2. So this one becomes the conjugate of this. And you can see that it is acting like a reflection. Are you okay? A reflection in the x-axis, or using the x-axis as what? A mirror. That is it. So this is what we are calling the Argand what? The diagram. Plotting them there. All right? Okay. Now, let's see another thing. We can also think of what? A complex numbers as a vector from 0 to a point AB. That's what we have said. Look at that. From 0 to here. Now we are going to talk about modulus and also the augment. This one is the angle that if I have this, and this is what I have. The angle that this is making with the positive x-axis, and we measure it anti-clockwise. So counterclockwise, this way. We measure it this way. All right, this way, not this way. When we measure it this way, it's positive. When we go the clockwise way, it becomes negative. The modulus is also like people call it the magnitude. So as we can find the magnitude of a vector and the angle it makes with the x-axis, here too, complex numbers can also be treated as same. All right. So when we are finding the modulus or the absolute value of a complex number, we represent it by what? This. All right. And it is defined as what? The distance between the point Z and the origin. So here, If I want to know from here the length or the modulus of here, I am measuring from the origin up to here. And we are going to use the rectangular formula or the distance formula to calculate whatever we want to calculate. Are you okay? To calculate whatever we want to calculate. So we are saying that the length or the distance between Z and the origin in the complex plane, where people call this one the length of a what? A vector corresponding to Z. Let's see how to do that. If I have this, okay, and I am finding the modulus of the complex number, modulus, so we bring this one, or the absolute value. We can write it as this, and it is like taking the square root of the square of the real part plus the square of the imaginary part. This is the formula we use. Are you okay? This is the formula we use. So if I have this complex number a plus bi, and we want to know the modulus of this one, we are finding the modulus of this is the same as the square root of a squared plus what? B squared. That will give us. It also follows that the modulus of a complex number is equal to the modulus of its what? Conjugate. So when I have also a conjugate and I want to find its what? Its modulus, I'll have it like this, which is the same as this, and it's also giving me the same as this. So when you give me the conjugate and you give me the complex number itself and its conjugate, and I'm finding the modulus, it should give me the same value. All right. Now let's look at this. The length, this, or the modulus, this of this vector is called the modulus. That's what we are saying. When we are finding the length of the complex number, we are terminating the modulus here. And there is a condition here that this is always a positive real number. All right. Like we are finding distance and your distance is negative. It's not true. All right. It's only physicists who can tell you that when a distance is negative, then they are measuring it in opposite direction, reverse direction. But for a distance or the length or modulus, we are saying that it must always be positive real number. Now we are also going to measure an angle, theta. Okay. This vector mix, when we draw, like I said, if I have this as a complex number, okay, from the origin, it will make an angle with the positive what? X-axis or the real line. Okay. And we are going to calculate it or take it anti-clockwisely. So that angle that we are going to measure, that angle we are saying that it is called what? The augment of the complex number base. And look at how it is written. Okay. So the arc Z is just asking you what is the angle between the line that is connecting that number, okay, the complex number, and the positive x-axis, measuring it anti-clockwisely. That is it. That is it. All right, so let's try. Now, this is what is given to us. Z is equal to A plus BI. Now, when we find the modulus, it is from here up to the point there. So this is the modulus. And this angle here, the shaded portion, that is what we are terming to be what? The arc of what? Z. All right, the arc of Z. Remember, this X is the real part, and this one, the vertical, is the imaginary part. This side will be the negative of the real, the down will be the negative of what? The imaginary, depending on where the complex number lies in the plane. All right. Now, we are saying that, like we have done this one, if we need to find the modulus of this, we can use this formula. All right, we can use that formula. And Z is equal to A plus B. Here, this one becomes the hypotenuse. Are you okay? it becomes the hypotenuse. Then the red line becomes so I have something like this. Here becomes the modulus. The real part is here. This one will be parallel to this. So this side here become the B here, and here is what? The A. So if I have Z here, the modulus of Z here, and I'm using the particular theorem approach, then it will be this square plus this square is equal to this square. All right. That is what we have. All right. And finding the modulus of Z, we use this one. All right. We use that one. Okay. Anything to add? Now, so we have this. Look at this. This is Z. This is its modulus from origin to this place. Using the particular theorem approach, this is A, this is V. So finding here, this side square is equal to this square plus this square. All right. And we can find our whatever. Now, the angle that we need, we say we should measure it like this. From the positive x-axis. So this will be 8. But we know from trig. Are you okay? I know from trig that I can find this angle, maybe alpha, using this size that I know. Then the real angle that I need, I know from this line to this line is what? Is 180. So when I get this one here, I can subtract this one away. Or this side here is the acute part of this angle. So if we know any property of an angle and it's acute, then we can also apply that one. So now let's see what we want to do. Okay, let me come here and let's all build something from here so that we understand what we want to do. Now, if I have this, let me say this, something like this. Here is A, here is B, here is C. This is my angle theta. I need cos of the angle theta. What should I write?
Adjacent to the hypotenuse, which is A out of Z.
Good. What of sine?
B over Z.
Out of A. B out of Z.
That will be B out of the modulus of Z. That is all what we want to do. Are we taught that anytime we need angle, proper angle, we should use the tan? And what is tan?
B over A.
B over A.
B over A. So you know that when I divide this one by this, it will still come and give me this, you know. All right.
Yes, please.
Okay. So we are saying that finding, are you okay? The arc of what do you call? The complex number, which is the angle. Then cos, we have said so. That will be the real part over the modulus. And we have also said this one, the imaginary part over the modulus. All right. There is something we should take note here. This is a unique solution to this equation. All right. We are considering the equation from negative pi up to positive pi. And all the angles there are called the what? The principal augment. Are you okay? The principal augment. Let me explain. Now, if I have this, let's see. If I have this, you know that here will be pi on 2. Pi on 2 is 90, right? And here is what? Pi. Here will be 2 pi. If I move from here, then I come back to here. I've moved 2 pi. Do you agree? 2 pi is the same as 360 degrees. Do you agree?
Yes, sir.
Yes,
sir. Okay. Now, I want somebody to point this one for me. What is sine 60?
It says root 3 on 2.
Root 3 on 2. That is correct. So let's take that here is the 60. So when I am measuring, I measure up to here. Now, if I should go so, this is the same thing. If I start from here and move like this and come back to hit the line, what will be that angle? Hello?
360.
300.
It's what?
360.
Is it no more than 360? Look at this. Look at this. I am
Okay.
saying
That is
360 plus
I have
420.
That is 420.
I started from here, then I come to also here.
420.
All right.
360 plus theta. 360 plus theta.
So it will be 360 plus what? Theta. Theta. So I am using this one, which is the same as 360 plus theta. What are you going to get?
420.
For what?
420.
420.
What is sine 420?
So the same as sine 60.
Okay. Now, if I do this, I start from here. Then I go. Then I come back. Then I come and hit there. What will be the angle? I went twice, isn't it?
840.
840. That one will be theta plus 2 multiplied by 2 this, isn't it?
Yes.
Yes, sir.
Yes, sir. Okay, so you see the angles that we are looking for, some of the angles we can go round and round and round, but still they will produce the same thing. Because of that, when we are finding the angles, we are restricting ourselves to just a complete circle. But we have to write a final equation where when you go around it 2 times or something else, you are still going to find the angle that you need. Are you okay? So this is what we are saying. For that reason, we are going to use the general term as this, that theta plus 2 pi and a k. The k is that maybe k can be 1 or k can be 0. If it is 0, then this one goes. Then we are measuring that angle that we need alone. If k is 1, then we are going to have the angle plus, meaning that I started here, I went around 1, and I came to end here. If somebody went through 2 times, k will be 2. Are you okay? So this one is going to be given us as the general formula to look for all the angles, because it is not only 60 that will give me the same that answer. You say 420 will give me. Are you okay? So there are so many angles that will produce the same answer as the 60. So we should have a situation or a formula which we can use to search for all the formulas or the angles that we need. But in this, we are restricting ourselves here to a principal one. We are saying that we are restricting ourselves to only negative pi up to where? Pi. This one. What is negative pi and pi? If I have this, when I go this way, that is pi. Here is pi. Here is 0. So I am going this way. Or I can go this way. Are you okay? When I go here, it's positive. When I go the reverse way, clockwise way, it will be what? Negative. Now remember, we are not up to going up to here. You see, when I'm going reverse way, it should be negative pi. The negative here is saying that I am moving clockwise instead of going anti-clockwise. And we wrote this here. Look at that. When we are given something like this, a close range or a range like this minus that, then pi also this. Then we are saying that it is equal up to this one, but this one we are saying that you are not part of the solution. Why are we saying so? When I move from here to here, it will land me to pi. All right. But when I am landing here, I shouldn't go so, because negative pi and pi itself, when I find the angle, it will give me the same thing, the same value. And because we don't want to repeat or get two numbers that will give the same angle, we are trying to concentrate on a circle like this. But we can measure this way, and we can also measure this way, but going this way, it should be less than this line. All the angles within this frame, this restricted area that we have. So we need 1, 1, 1, 1 angle, not the other ones. So the ones that we need within the circle is what we are calling the principle of what? Or the principal augment. And look at that. The general one, we represent it with a small a, RG. But when we need the principal, so we said here that there is a unique solution to this equation between negative and positive what? Pi. All the solutions, the theta within that range is called the what? The principal augment. And look at that. We are representing it with what? Capital A. Are you okay? Capital A of Z. The principal augment, that is this one, is not the only angle that satisfies the equation above. There are infinitely many angles that do. They are of the form this. Are you okay? So we know that this principal we are calling the theta. We can add other things, this formula. The principal plus 2 pi k. Are you okay? Where k is a member of its integer. When we use this one and we begin to change k is 0, k is 1, it will produce a lot of what? Angles that will give us the same answer as that of the principal. But for our interest, we need only the principal. So the principal one, we represent it with capital what? A, but the general one, okay, the general one, we are using it to be as what? Small a. So any augment, this, of G is in this set, or this one become a very big set, that every angle there will form there. But our interest is not to build, to look for everyone. We are looking for those that are within the range negative pi and this. And by that, we are saying that we are looking for principal augment. Okay? This is the theory. Let's see example and you understand. Now, when we look at this, all right, first we need to plot. So we are plotting this one. The real part is 1. Are you okay? Then the imaginary part is root what? Root 3. Now, this is it. So we plot it, and that is it. We need the modulus of it. That's the modulus. So finding the modulus, we had the modulus to be what? 2. Now that we know we need the modulus, we have gotten the modulus. Now we need the augment. And let's see. So we are saying that the principal augment with the capital is a unique solution where theta falls within this range to the equation. So we have found this already, and you told me that cos theta is equal to the real part over the the hypotenuse side, and this is also, we have found it. All right, now let's fix the values inside. We need A over the modulus. What is A? A is 1, the modulus is 2. So that cos theta will be equal to 1 over 2. That's what we have. And also sin theta will also be B over the modulus. That is this. All right. Now I want us to point this one. Cos 1 over 2 is what? No, find theta for me. Find theta. If cos theta is equal to 1 over 2, what will be theta? Find the cos inverse. Any answer?
60 degrees.
It's what? 16 or 60?
60 degrees. 60.
Okay, 60 degrees. Good. Now look at this. We are saying that this angle that we are measuring, these angles are measured in radians. The degrees ones are conversion ones. So let's convert them into what you call radian. Now it's the same.
1 over 3 pi.
1 over 3 pi. Good. So this one produced 1 over 3 pi. That's what is here. All right. And so the argan, the angle that we need is 1 over 3 pi, or pi on 3. Okay, pi on 3. This is the principal one that we need. But remember, this is not the only answer that it will produce. So we are saying that it's possible that when we have this, are you okay? 7 pi on 2 on 3 is also one of the angles. Negative what? Pi on negative 5 pi on 3 is also another one. I am using the general formula for you to see where the 7 is coming from. We know the general formula will be the argan, which is theta plus 2 pi what? K. Where K, we said it can start from maybe 1, 2, and 3, and 4. Okay. When K is 1, then it means that this whole thing is 1, isn't it? Hello? Hello?
Hi. Yes, sir. Yes, sir. Yes, sir.
So this one is the general formula. All right. So if we know this argan to be pi on 3, what is pi on 3 plus 2 pi? What are you going to get?
Seven pi over 3.
It's 7 pi over 3. Are you okay? And 7 pi over 3 gives the same answer as 3 pi on 3. All right? It gives the same as pi on 3. Are you okay? So that is great. That is it. Are you okay? So and this one, when I write pi on 3 minus 2, the minus is that I went this direction, not this direction. I went this direction rather. So I am subtracting pi from it. When I do this one, what will I get? Pi on 3 minus 2 minus
negative 5 pi over 3.
That is it. Are you okay? That is it. So all these ones will produce the same answer. But our interest is to work within pi and what? What do you call negative pi? So this is the argan that we are looking for. Don't go there to worry yourself. When you get this one and this one, who to produce the same answer, you just find them in degrees. Are you okay? Degrees. And when you finish, you convert them into radiant, and that will be your argan for you. All right. Okay.
So please, that one.
You said?
I have a question, sir. So, is it that the only different K for you, or you have to choose what your K is?
Oh no, the general one. The general one, we are not using the general one. So your K. You can choose K for yourself when it is going around several times, but we don't want to go there. We are just trying to tell you that there are other solutions which will be the same as yours. But our interest here is we need the principal. Are you okay? The principal is that what is the theta? So find the theta for us. Are you okay?
Okay, sir.
Are you okay?
Okay. Yes, sir.
But I was just telling you that the principals are not the only answers. There are other angles. But the question, our interest here is to deal with the principals. So that is it. Now let's look at this.
Sir.
Yes.
This when the complex equation is given to you, do you treat A as the real number and B as the imaginary number?
Yeah, that's what you have to do.
Okay.
Yeah. So now find the modulus and the augment of each of the following complex numbers. Hello. So look at that. And this. What do we have to do? First, we find the modulus. Then after we have the modulus, we try to construct cos theta or the cos of the argan and the sine of the argan. Okay, of u. Then through that, we'll get whatever we need. So let's take A. U is 3 plus 4i. Let's see the solution. We need the modulus of it. That is root of 3 squared plus 4 squared is equal to 25 squared, which is equal to this. Now we are saying that A is equal to 3, which is greater than what? 0. B is also greater than 0. Are you okay? And when we plot them, look at that. 3 will be here and 4 will be here. So it is in the first quadrant here. When it's the first quadrant, we go straight. We don't need any other thing again. So what do? We are finding the cos. Are you okay? But I told you that tan is all the time what we use in finding the trick. Tan. So look at that. Arctan is what we are using. So tan theta is equal to what? That will be adjacent over hypotenuse, opposite. That will be opposite over this. So that one will give us 4 over 3. Are you okay? So when we find the angle, we are going to get this. What is tan inverse of 4 over 3? Tan inverse of 4 over 3.
53.1.
53.1.
That one is in radian, in degrees.
53.1.
In degrees.
Yes, that's in degrees.
Okay, in radian.
The answer is 0.9272.
That is it. So that is what is there. Are you okay? That is what is there. Good. All right. Now, let's look at the second one. Now we have 12 and minus 5. 12 and minus 5. So 12 is here, minus 5 is here, tells that that thing lies here. Somewhere here. And it is lying in what quadrant, please? This
The
is
second
first
quadrant.
This is first, second, third, and fourth.
The fourth.
Are you okay? Fourth quadrant. Okay. So if we are measuring it here, remember that they say we should go so up to this place. And all right? Okay. Now look at that. If I should go so or somebody goes so, this one is a positive up to this place, this way. Are you okay? And minus this. Now, this is what we are saying. For us to be able to deal with the fourth quadrant, then we are going to use this. Like we go a complete one. Look at that. If I know that, let's say here is 60. Hello, here is 60. What do we from here up to here?
300.
300.
What did you do?
So I
Subtracted
subtracted 60
from 360.
from 360.
That is all. That is what we have done here. Look at that. This 2 pi is 360. Are you okay? And we need what is here. So we model that one and subtract it from 360, and we are going to get our answer. That is it.
Okay, so in between 920.
Are we there? Are we there?
Sir.
Yeah.
Sir.
Yes,
Why
please.
didn't you use the tan, the angle, the tan, as we did for the first one?
All right.
So that
look at this. And so that
so in the first one, we looked for tan. As you said, the sine and the cos will always come out with a tan. So in the first one, look at, we found the tan at the opposite over the adjacent. I thought we were going to do same for this one also.
Okay. Yeah, that's what we did. So look at that. Look at it. We did the same thing. And you should understand this one for me. This is what I'm doing. So when I do this is it. Are you okay? Here is 12, right? And here is minus what? 5. You agree?
Yes, sir.
Hello?
Oh,
Okay.
yes.
Now, this is what we want. The angle that we need is from here up to this place. That is the angle that we need. But what can we do? We can use this small triangle, this one and this one. We can use it. So we write maybe here is alpha. Then we can construct a triangle here using this one and this one. We find a triangle here. That triangle here is minus 5, and this side here is what? Is 12. Now, what is tan alpha? Tan alpha is what?
Negative 5 over 12.
Minus 5 over 12. So if I need this one, alpha, are you okay? It will be the tan inverse of minus 5 over 12. It is theta that I need. It is not alpha that I need. Are you okay?
Yes, sir.
Hello?
Yes, sir.
So for me to get theta, then theta here should be equal to the complete one, which is 2 pi minus alpha. Are you okay?
Yes, sir.
And this one, we know that it is the tan inverse of minus 5 over 12. So this is what we are calling the argan of Z. It's equal to 2 pi minus that. So that is what we have done. Are you okay? It's the same thing.
Sir.
Yes, please.
Hello.
Yes.
I've understood this perfectly, okay. But in your earlier submission, you realize that we came across a general relation whereby we said is it theta plus 2 pi k. And I bet you differ. You said we are not supposed to go there. Is that not it? Because you were just trying to tell us that apart from the principal angle, we have other angles. Is that not it?
Yeah.
But looking at this, it's like we are bringing back the general relation, or
okay, no, it is not the general relation. Okay, yeah, it's the general relation. Let's see. In it, I'll agree with you, but let's see. You see, what we said was that, okay, what we said was that, look, another form of writing this one, this, is the same as we are writing that, okay, the this one, fall between 2 pi and what? 0. So we need angles between 0 and 2 pi. Maybe I didn't write this one, so you didn't see. Anything that will go beyond another cycle, we don't want to talk about it. Are you okay?
Okay.
So we need angle within one cycle, not to continue and continue. We can have just all angles within this one that will be equal to whenever you go around the 3, we go around the 4. Are you okay? So in that case, all right, if we want to go around it 1 plus something, that is where we write this one plus. This one is saying that I have gone round once and adding something to it. Are you okay? Are you okay? But
Yes,
even the angle that I need is within the cycle, but which is even not up to the cycle. So how do I get that one? If the whole cycle is 2 pi and mine is somewhere here, then like this, then it should be from here up to this place. How do I get that? With the help of this line and this line, I can rather find the small angle here. So if I am able to find a small angle here, which that is not what I want, but I need from here up to this place, then I will subtract this one from the complete one so that this one will be I'll have it. Are we clear?
Yes, sir.
All right. Okay, so that is
it.
So that is what we did here. All right. In the same way, look at this. We are also having this one. Look. B is positive here. X is negative, meaning that it will be here. We need this angle. All right. So what do we do? Because of this line and this one, we can find the triangle here and find the angle which is here. This small one. When we subtract this small angle from 180, we'll be able to get what we want. Are we clear? Are we clear?
Yes, sir.
So that is what we are doing. That's what we are doing. Okay. Now, when we check this one, negative, negative, meaning that X is negative, Y is negative will be here. Look at that. So what do I do? This line and this line can form a triangle here so that I find the small angle here. But the angle that I need is from this R to this. So once I am able to get here, I'll add this side to this small one. Then it will give me the angle that I need. So this 180 here is pi. And this small angle that I set was here. So adding this one to the 180 here gives me the angle of what I want. All right. So that is it. And it is like this. Look at this. If X is 0, Y is 0. And X is 0, Y is what? 4. Like this. Then it means that it is this line. Here is 4. And what is this angle? What is this angle?
90.
It's 90. So pi on 2 is 90. Are you okay? Pi on 2 is 90. Now, if I have A to be 0 and Y to be minus 3, it's this line. Now, moving from here up to here, 90 plus 90 plus 90. Are you okay? It is like, so look at that. 270 is 3 pi on 2. That is 90 multiplied by 3. And that is it. Are we okay? Are we okay?
Yes,
Sir,
sir.
please, can you go over it once more for me?
I am saying that if I should plot this, all right, that one is going to give me this. All right, it's going to talk about x is a is 0. If on the line, if x is 0, we are talking about the y-axis. So this is what we have. So this is somewhere here. When we plot it here, this is, if I should plot it, it will be 0 minus 3. That is this line. And we need the angle here up to this place. And we are saying that here is 90. Here is also 90. Here is also 90. If 90 is 3 pi on what? On 2. Then 3 of it will be what? Is not 3 multiplied by 8? Are you okay?
Yes, sir.
So from here up to here is that.
So, sir, is the power on 2 constant?
Pi on 2.
Is it
constant? Oh, it's like somebody is writing 90.
Oh, okay.
Here is 90. Here is 90. So I am just saying that it is 270 degrees. Are you okay? So if you want to write it in degrees, you write it is 270. But I want to write it in radians. So I write it like this. Are we there?
All right, sir.
All right.
Thanks.
Good.
But sir, we are supposed to work in radians, right?
Yeah, that's what we are trying to do. Because angles were measured in radians, and we are converting them into degrees. All right. So the slide there made some. You will see it measures something here. Augment. Where is it? They say something here. Let me see. Was it here? Let's see. Augment.
Sir, but why are you pronouncing that word as augment?
How do you pronounce it?
Yeah, I'm seeing it as argument.
Exactly.
It is silent. It is silent.
Okay.
Augment. Okay.
Okay.
All right. So we said here that, look at that. The angle theta always in what? Are you see it? Yeah. Are you okay? That is it. That is it. Okay. But when you write it in the other one, you are not wrong. Okay. You are not
Sir,
wrong.
please, Hannes.
Okay. Yes, please.
I would like to ask, after plotting the points and where the quadrant that our graph will fall will determine the trig radians we are going to use to find for the theta.
If you use any other apart from tan, then you have to look at where you are standing. Are you okay?
Okay.
Jack,
That's
where
what
are you? Yeah. If you don't use tan and you want to use any other thing, then you have to ask yourself, where am I standing? Are you okay?
Okay.
That's why I told you that tan is the universal one. When we are teaching in the basic school and they are finding acute angle, we tell them to use what? The tan to do it. And that one shorten is fast. All right. Okay. Now look at that. I have somebody here that's a complex number and another complex number. And I want to find the distance between them. Distance between two what? Complex numbers. All right. Distance between two complex numbers. How do we go about it? All right. How do you go about it? Today, I'll give you about 15 minutes off to recharge your machines, okay? Then we'll come back. But I am not there yet. So when I get there, I'll tell you. Yeah. Now, let's see. We have Z and W. We want to find the distance between them. So what we do is that we try to form a right angle triangle. And look at that. The distance we are finding is that you are here. I am here. What is the distance? We do this. When I come here, this is your building. This is my building. This is the distance. We are not interested in this one. We are talking about this. If this one should be a building, and this one is also a building, what is the distance between them? Are you okay? All right. We can do that. Or we can as well also take this one as one of it. But let's see. We need to plot what is given to us. Where is Z? Z is A here. Are you okay? A here against B. And B is here. So that is it. Then W. C on the real and D on the vertical. So that is it. Okay, now what is the distance from me to you? Let's use this one. All right, what is the distance between you and me? We can use the distance formula like this, but look at that. Somebody is saying that Z minus, all right, so let's do this. Let's use the vector approach. Let's use the vector approach. If I have this and that, let's say that we are going this way. The vector is moving this way. All right. Therefore, this one will be this way. If here is A, here is B, here will be C. All right. Then we know that C will be equal to A plus B. Right? Okay.
So if it is vector approach, okay. Positive vector. I get it.
Resultant vector. That's a resultant vector.
Resultant vector, yeah.
Resultant, yes. So if now my angle is like this, if I change the angle like this, this one is going so. What do you think will be?
It will be B plus A.
Negative C is equal to B plus A.
Negative C is equal to B plus A. This one. Okay. At what time are we going to say that? Hello? C plus A is equal to B.
Hello, sir.
Yeah.
Sir, please, the negative C, B plus A. Can you still make it negative C, A plus B?
Yeah, it's the same. But I am asking, at what level are we going to have this?
Sir, please, when the arrow is on the B.
When arrow is on the B.
So when B is the resultant.
When the arrow is on it.
Okay. Good. Now let's see. I just want you to understand something here. So what I'm saying, you understand everything there. The distance, we need the distance. Are you okay? A and B. Now let's go to geometry. If I have a point here, vector is there, geometry is there. I have a point here, A, and it is x1, y1. I have also a point here, B, and it is x2, y2. What is the distance between A and B?
District.
B minus A. B minus A.
That will be B minus what? A. This one. So when we do this,
Small B. Small B.
then that one become S2 minus S1 all squared. You remember? Plus Y2
Yes, sir.
Y1 all squared. You know that?
Yes, sir.
Yes, sir.
That is what we are using. So we are using the coordinate geometry approach. That when
Sir,
we are
someone
coming,
microphone.
hello,
There's
the
feedback.
microphone should go up. When we need the distance between X and Y, a Z and this. All right. So let's take this one maybe to be B. Are you okay? And take this one to be maybe A. Or whichever. We are subtracting one from the other. Meaning that their coordinates will be subtracting from the other one. So if we take Z minus what? W. Then we will subtract the real of the W from that of the Z, like this. And we also have this one. But remember, we are talking about magnitude or the distance or the modulus. So this is what we are going to get. Using the distance formula, we have this one. All right, we have this one. So this is the distance formula we know already, and we are using the same thing. That idea was used using Pythagoras theorem, but it's basic, so you should remember, it's basic. Anytime I am finding the distance between this one, I'm subtracting this from this. Whatever I get, I take the modulus of it. And that is what we have done. So using the complex itself, now I take the modulus of it and I'm getting this. So we said by using what? Pythagoras theorem, this is precisely the distance between 2 points A, B, and what? C, D in the plane. This will represent the distance between the two complex numbers Z and W. And we can use this notation to describe shapes and lines in what? Complex plane. All right, in the complex plane. All right. So the next thing we are going to talk about the next 15 minutes. Are you okay? Is this time how to also write this one, complex numbers in the polar form. All right, in the polar form. We said this one is written in the Cartesian form. We are able to find the modulus. We are also able to find the argument, okay, within or the principal ones. Now we need the two to be able to rewrite this one in a different way, where we are going to call it the polar form. So by my watch, what is the time now?
9:23.
9:23. So the next 15 minutes, we'll be back. Okay, we'll be back.
Yes.
All right. So charge your machines and let's continue from there.
The light has not come.
The light has not come.
Yes, please.
So what are you going to do?
Mine has come.
Let's continue
Hey.
then.
Yours has come. Mine has not come.
You are not lucky. Mine has come.
Mine has not come.
So
So
please,
and
let's continue.
my machine, my phone is my computer is almost red already. So in the next, it will be off. All right. So let's take that round. All right, and see if somebody can get a charger from somewhere or another machine.
Okay.
From their wife or from my friend. All right.
20 minutes. Make it 20 minutes. 20
so
15
minutes.
minutes.
20. 15 will be okay. Let's see.
Yes.
All right. Okay. So thank you. Thank you. All right. Yeah. Bye. 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 Bye.